Today's topic is Benkeser reduction and diimide reduction. In the diimide reduction, I'll be dealing it with the catalytic hydrogenation part. Okay, so there will be again two types, that is your homogeneous and heterogeneous catalysis. So moving on to Benkeser reduction, this Benkeser reduction will be continued from your or dissolving metal reduction part. Okay, this Benkeser condenser and Clemmensen reduction and will be there in the dissolving metal reduction. So let's begin with the Benkeser condensation, Benkeser reduction. What do you mean by Benkeser reduction? Benkeser reduction is the hydrogenation of the polycyclic aromatic hydrocarbons. That is especially naphthalene is taken and in the presence of the metals such as lithium or calcium, using the low molecular weights, alkyl amine will act as your solvent. When the alkyl amine is acting as a solvent and it in part as the source of the protons, then the reaction will takes place by the formation of your hydrocarbon in products. Okay, so when the naphthalene is converted into the enes, that is your 1,6-ene or 1,2-enes bicyclo compounds of your enes, all the double bonds are getting reduced by leaving only one bond in between, that is your in the 1,6 position and or in the 1,2 position. So with this respect to this position, whatever the product you are getting, in the phenomenon which is happening in this reaction is known as your Benkeser reduction reaction. Okay, this reaction will be the modification of your Birch reduction, which I have shown you in the earlier, that is your or electron transfer reactions. Okay, and then this, what is the advantage of doing this reaction? So this reaction will offer the a greater advantage is for the conduction of the temperature. At high temperature you can conduct by the boiling point of your ammonia, that is your minus 33 degrees Celsius of your boiling point of your ammonia. By using that solvent you can conduct this reaction at high temperature. Okay, then this is your Benkeser reduction. Mechanism is not required, so only reaction is given and I have dealt with the reaction part. Okay, and then moving on to Clemmensen reduction, you can go through this link for the Clemmensen reduction, which I have done in the earlier videos, that is your Clemmensen reduction part. Okay, and then moving on to next slide, that is your diimide reduction. The diimide is nothing but it is the N2H4. Okay, N2H2 diimide, that is your or two imide compounds N2H2. So here what is your diimide? Diimide is an unstable compound, highly unstable, and it is generated in situ. That is in situ means the reaction mixture which is taking place inside the portion. Okay, so whatever you are doing within itself is that reaction is known as your or diimide in situ reaction. And okay, you can use this in the various fields also, geological and biological as well. And then moving on to next point, it is highly selective reagent and for the reduction of the double bonds or triple bonds, that is your alkenes, alkynes and nitrines, then oxides and disulfides. Okay, so this double bonds can be reduced to the single, triple bonds can be reduced to the double bonds, etc. And it is also an here what happens, unsymmetrical unsaturations will not be affected by using this diimide reduction reactions. In the presence of unpolarized alkenes, alkynes or allenes, the diimides will in the presence of the diimide reagent, that will convert into the dinitrogen and with the reduction and of the unsaturated functionality. Okay, and moving on to reaction part, if you are taking the hydrazine, and then if you are treating the hydrazine, when the hydrazine is treated with hydrogen peroxide at room temperature, diimide is formed by the cleavage of water molecule. Okay, if we are taking the tosyl hydrazine in and upon heating, in the N2H2, that is your diimide is formed with the cleavage of your or tosyl hydride. Alright, that is your preparation part. So moving on to mechanism. So here you are taking the N2H2, that is your diimide, and then you are treating it with the alkene. If you are taking the stereochemical aspect, that is the stereochemically, if you are showing the alkene part, okay, so here what happens, the hydrogen, the attack of the alkene to the hydrogen, the hydride transfers, okay, this is going and attacking to the hydrogen, and then this is bond is shifting over here towards here, and then again this bond will go and attack to the alkene. That is you are generating one of the transition state. 6-membered cyclic transition state is generated. It followed by the cleavage of your or nitrogen by the formation of your hydrocarbons. Alright, that is your C2H5 C2H6 is obtained. And then moving on to diimide here what happens here is there is the reaction which is proceeding through this part is, it is only syn addition or the cis addition. Alright, and then here are some reactions which is shown sterically with the free phases of the olefins. If you will take the first compound, first example, here if you will see this bicyclic compound on is having the exo free nature, okay, exo free phase. So if you are treating it with the N2D2, okay, deuterium compound, and so this alkene gets deuterated and this bond is getting reduced by the formation of two bonds over here by the addition of the D, okay, deuterium, rather than the hydrogen. We are adding the deuterium compounds and we are seeing whether the reaction will go or not. And then if we are taking the alkynes, and in the presence of N2H4, that is your or hydrazine in upon addition of the hydrogen peroxide, right, here what happens, the alkynes are getting reduced to the alkenes, and again here with the addition of the hydrogen compound in the presence of upon heating and in the presence of the diglycine and the substituted carboxylic acids, okay. So here amide substituted carboxylic acids, here what happens here is the addition of the hydrogen will takes place. Moving on to catalytic hydrogenation. What do you mean by catalytic hydrogenation? So catalytic hydrogenation is nothing but the hydrogenation of an unsaturation with the hydrogen and in the presence of the metallic catalyst, okay. Here the catalyst is used, catalyst is the enhancement of catalyst is used basically for the enhancement of the reaction, and so this phenomena is known as the catalytic hydrogenation. We are adding the hydrogen to an unsaturated compound and in the presence of the metal catalyst, that is known as your catalytic hydrogenation, okay. So there are two types of hydrogenation. One is your heterogeneous hydrogenation, the other one is your homogeneous hydrogenation. So if you will see in the next point that all the types of unsaturations will be reduced in the presence of the catalyst, that is your catalytic hydrogenation, including the aromatic skeletons, that is if you are taking the aromatic compounds such as your benzene, naphthalenes, anthracenes, phenanthrene, etc. That unsaturation, that is your double bonds, will get reduced in presence of the catalyst such as nickel, palladium and platinum catalyst, etc. Okay, so here if you will take this compounds, for example we have given this compound such as your alkenes, alkynes, nitriles, nitro groups, and then benzenes, and then esters and the CO C double bond X halide compounds, acyl halides, okay, acid halides compound, etc. And then moving on to hydrogenolysis, here you can see the process over here. This is for your or heterogeneous hydrogenation, okay. this process, if I have to show you, it is for the heterogeneous hydrolysis process. Let me explain you this pictorial representation. And so here is the surface. Okay, this is the surface, and you are adding the alkane, and the hydrogen is going and binding over here. In the first step, the alkene bond will go and bind here. Okay, when the alkene bond goes and binds here, then what happens here is, this is your first carbon. This carbon will slightly go and take this proton which is attached over here, which is adsorbed, adhesion which is taking place. Okay, which is adsorbed. You know the difference between adsorption and the absorption. The adsorption is nothing but, if I have to take an example, like if we are writing in the board and the chalk dust has been fallen into your shirt. So what happens here is, that is just the chalk dust is just going and sitting towards your shirt. That is your adsorbed. Okay, adsorption which is taking place. It is just going and sticking. Instead of that, if the water falls on your shirt, okay, so what happens, there is the absorption which is taking place. You feel wet, you will feel wet, right? So that is your absorption process. That is your adsorption process, is nothing but, it is just an adhesion. Okay, it is just a sticky material to the surface. So here what happens, the hydrogen which is binding to the surface, the carbon will just go and take this hydrogen, and so once the first carbon which will take the hydrogen from the surface, in the first step it will just go and attack. Okay, it will adhere, and in the next step, if you will see, this carbon is taking the hydrogen, and then it is slightly moving towards itself, like it is just going in from the sphere. Okay, from the surface it is just trying to move, and then the second hydrogen which is sitting over here, or again the next carbon atom will go and try to adhere that one. It will try to take away this hydrogen, and slightly it will cleave out, resulting you in the hydrocarbons. Okay, that is your heterogeneous hydrogenation process. Alright. Okay, let's begin with the hydrogenolysis. So here hydrogenolysis, what do you mean by hydrogenolysis is the breaking of the sigma bond by doing the hydrogenation reaction. So here what happens, by addition of the hydrogen molecule, okay, by the addition of the hydrogen molecule, well, in the presence of catalyst, the sigma bond is broken. It is cleaved out. That process is known as hydrogenolysis. Okay, lysis is nothing but breaking. So breaking of the sigma bond by doing the hydrogenation and using catalyst is known as your hydrogenolysis. So here is the reaction. If you are taking the CX bond and then you are adding the hydrogen. Okay, so here what happens, this hydrogen will go and bind to the X, and here also this carbon will take the hydrogen from here. Okay, so meanwhile what happens here is, there is the formation of this bond, and once it is formed, once these bonds are formed, and again upon hydrogenolysis, that is the breakdown of the sigma bond towards this side, that is CX bond is broken to get your hydrocarbons. Okay, that is your hydrocarbons is formed. Here you can satisfy the carbon atom by adding the bonds homogeneous and the heterogeneous catalytic hydrogenation. This reaction. So this homogeneous is nothing but the catalyst which is soluble in the solvent, and then in the heterogeneous it is insoluble in the solvent. Alright, and here the catalyst must be with the organic group which is readily soluble in organic solvents, such as here we are using the Wilkinson catalyst, that is your trisphosphine in chlorotrisphosphine rhodium 1 complex. Okay, so that is your Wilkinson catalyst, and then the alkynes will undergo hydrogenation, and stereochemistry will be based on the cis or syn hydrogenation, which is easy to predict the stereochemistry. Okay, moving on to heterogeneous, the catalyst is insoluble in solvent. Here you are using only the metals that is your metal oxides and metal sulfides, which are used for the heterogeneous compounds. No organic groups will be used in this catalyst, whereas here you are using the organic solvents, that is you will read this catalyst in the OMC compounds. Okay, in the first unit you will use this Wilkinson catalyst, and this there you have the mechanism as well, which is an important reaction over there. And here if you will see in the heterogeneous, you are using only the metals, that is here, or platinum oxide, nickel, palladium, platinum and tungsten, etc. And all the unsaturations will undergo hydrogenations. That is, for example, if you are taking the carbonyl compounds, alkenes, alkynes, nitrides, nitro groups, etc. Okay, this can be reduced, this can be hydrogenated, and here it is very difficult to predict the stereochemistry in the case of the heterogeneous. In the homogeneous, very easy to predict the stereochemistry. In the heterogeneous, it is very difficult to predict the stereochemistry for finding the products as well. It is almost syn, but variations will be observed. This syn addition will take place, but there are certain variations which can be observed while doing these reactions. Okay. So moving on to next slide, here you can study individually what do you mean by heterogeneous catalytic hydrogenation and homogeneous. So here let's begin with the heterogeneous catalytic hydrogenation, and here what happens, as I have said you, that metals which will be used, that is your platinum, palladium, nickel, rhodium, rubidium, iridium, tungsten, etc. These metals will be used, and the platinum in its oxide, that is your Adams catalyst. Platinum oxides will be known as your Adams catalyst, which will be used for the hydrogenation of the aromatic compounds as well as the nitrile compounds. Okay, and then palladium will be mostly used in industries, palladium catalyst. Rosenmann's reduction you have studied earlier, in that reduction you are using certain catalysts such as your palladium, hydrogen or the barium carbonates, acid chlorides to aldehydes. It will reduce the acid chlorides to an aldehydes compound. And then Lindlar's catalyst, that is your combination of your palladium, calcium carbonate and lead oxide. That will be used for the conversion of your alkynes to the cis olefins. And the copper chromate, that will be used for the reduction of your esters and amides to an alcohols and the amines compound, okay, respectively. And then Raney nickel you have studied earlier also in the reagent chapter, that solvents will be used as the polar solvents we are taking as the ethanol, methanol and the acetic acid over here. Okay, let's see the mechanism which I have said you earlier also in the catalytic hydrogenation, that slide. Okay, so here if you will see, this is your surface and then these are your active sites which is attached. So in the active site you are taking this alkene, and then if you are attacking to the surface, okay, and then here the hydrogen is sitting over here. So once the alkene will go and bind to the hydrogen slightly moves and comes and bind to the surface. Okay, after the binding takes place, it will form one slightly coordination will takes place over here, or by the formation of your 4-member transition state, cyclic transition state, upon cis addition. Okay. So here what happens, this bond goes and attacks over here, and then this will comes and binds towards here, and then cis addition will takes place. Upon cis addition, well, first there is a formation of transition, and slightly it will try to leave this sphere and resulting in the formation of your hydrocarbons in the 4th step. Alright, only you have to remember this mechanism as first the active site will be there here, and then first you have to show the active site, and then you have to show the surface in which the alkenes are going and binding over there, adhesion taking place and the hydrogenation is taking place over here. Okay, and then there is a cis addition by the formation of your cyclic transition state, and slightly these molecules will get cleaved out. It will leave this sphere, or it will leave this sphere of this by the resulting you in the hydrocarbons as your product. Okay. So here are certain points for this hydrogenation, that is with increase in the alkyl substituents, that is if you will see here, at the olefins. You are taking the olefin compound. With the increase in the alkyl substituent, the rate of the catalytic hydrogenation will decrease. So by the decrease in the alkyl substituent, that is your simple alkenes, if you are taking in CH2 double bond CH2, if you are taking this ethene molecule, well, what happens here? The hydrogenation and will increase, whereas here if you will see, the hydrogen will decrease. This is your priority. You can check this priority over here. Okay, and then moving on to reduction of an alkenes. In this, alkenes is the easiest and it will takes place in the milder condition, and which is frequently used catalyst such as we are using the platinum, palladium or randy nickel as your catalyst to reduce the alkenes into the hydrocarbons. Alright, right. So if you are taking this compound, in the middle you can see the alkene bond is present. The hydrogenation which is taking place by the reduction and reaction in the presence of randy nickel or by the addition of the hydrogen in the presence of the organic solvent, polar solvent, ethanol. So here what happens? This bond gets reduced by the addition of the hydrogen atom, and then again if you are taking this compound, aromatic compounds, so here again dimethyl substituted cyclohexene in the presence of the hydrogen or platinum oxide, and upon the addition of your acetic acid, this bond gets reduced by the formation of your cis product. Okay, cis dimethyl product. And then again if you will see here in this next example, by the addition of this catalyst, platinum oxide or hydrogen in the presence of acetic acid, right? So again this bond gets reduced by the formation of your this compound. Here the hydrogen is adding from the back side, so we are showing the back bond. Okay, that is your dash bonds. And then again if you are taking the alene compound, this is your alene compound, or you are taking the limonene as your example for the alene compound, and in the presence of the platinum oxide or upon hydrogenation, and here this double bond gets reduced by the formation of your CH3, that is your limonene is getting reduced to the paramenth and 2-ene. Moving on to homogeneous catalyst for the homogeneous hydrogenation, and here Wilkinson catalyst is used, that is your tris triphenyl phosphine in tris triphenyl phosphine chlororhodium 1 complex. This is your structure of the RH PPH3 thrice Cl. Okay, so here you can write the Cl. Here you can write this as the chlorine over here. Okay, and then if you will move on to the mechanism, here you are taking this rhodium complex, that is your tris triphenyl phosphine chlororhodium 1. Here in the first stage it will be in the +1 oxidation state. Rhodium metal will be in the +1 oxidation state, and upon addition of the hydrogen molecule, it will undergo the oxidative addition. So here when it will undergo the oxidative addition, one of the triphenyl phosphine gets cleaved out. Okay, phosphine gets cleaved out. One of the one of the PPH3 will get cleaved out by the addition of one of the hydrogen over here. And after the addition, there is the complex formation, pi complex formation. So here what happens during this stage is the +1 is getting +1 to +3. Okay, oxidation state will we will get from the +1 to O+3. And after the addition of the alkenes, here there is a formation of the pi complex between the metal and the alkene. So you will show it over here. This is your pi complex. Next, and then within the molecule the reaction is taking place. This hydride will go and bind to the carbon atom of an alkene, and meanwhile it will shift and make a bond. That is migration of the hydrogen and to the carbon atom will takes place by leading to the formation of your or this compound. Okay. So the migration will takes place, that is your hydroid ion transfer or hydride ion migration, and after the migration step there is a generation of this compound, and then this bond shifts over here, and then first what happens here is the hydride transfer. Again in the next step there is a hydride transfer. This hydride from the metal will go and bind to the carbon atom. Meanwhile there is a cleavage of this metal atom, and then this will again regenerate to the solvent. That is the regeneration will takes place, and this will again come back to the +1 oxidation state. Okay. From +1 it is going to the +3, and again upon treatment with all the formation of your pi complex and with the cleavage of your hydrocarbons, hence it is getting back again to the regeneration step, followed by the formation of your +1 oxidation state. Okay. So unlike the heterogeneous catalyst, the homogeneous catalysts are highly chemoselective, regioselective and stereoselective reactions. This you have to remember this point. Okay. Homogeneous catalysts are highly chemoselective, regioselective and stereoselective reactions.
Moving on
okay.
to next point,
And then
here
here
are
if you will
certain transition
see,
metals,
you are taking an
transition
alkene
state, sorry,
in
not
that is
transition metals,
transition
substituted
state
alkene,
and
and
then
then
due to the close
the
proximity
deuterium,
of the
and
rhodium
the
metal
this
hydrogen
rhodium
complex.
catalyst.
Okay, this is your metal and
Upon
rhodium,
treatment of your benzene.
and hydrogen
So
complex.
here you are getting the mesoform
So
product.
here the
Okay.
unsaturated
That
carbons,
is
here
your
we are
one
taking
of the
an
reaction
alkene.
which is shown for this
In the
sentence.
first
Okay.
transition state it will show the half of the complex. Okay, half face of your or double bond can be shown in the first transition state, and in the next transition state what happens here is it will just go and attack to the carbon atom by the cleavage of this complex, that is your RH, and one of the H bonds gets cleaved out, so you are resulting in this. And then again in the third step what happens here is there is the formation of the bond on between the rhodium carbon and the hydrogen and the carbon atom. Okay. So that is your third transition state, and finally by the attack of the solvent, that is your ethanol or methanol organic solvents, polar solvents, by the attack of that solvent syn addition will takes place. That is this is addition. Syn addition will takes place is towards the one phase. Okay, that is your one phase. If it will takes place, then you are resulting in the syn product. Okay. And then this fourth transition state can be regenerated again for the rhodium catalyst. And then in the next, if we will show the transfer of the hydrogen at less substituted its site, that is this is your less substituted alkene. So hydrogenation will take place over here. If the hydrogenation will take place towards this compound, that is your CH2 double bond on again double bond CH. Okay, this part, this terminal alkene is getting reduced. Here if you will see, this is the highly substituted, because here you can see the alkene is attached with the dimethyl compounds as well as this moiety. Okay, so here if you will see the terminal alkene, this is only attached with the carbon towards the adjacent side. Okay, so upon treatment with the Wilkinson catalyst, it's this alkene will get reduced to the hydrocarbon. And then in the next reaction, if you will take this compound, this as a starting material, the deuteration will take place again in the less substituted compound. Here if you will see this alkene, it is highly substituted with this molecule. Okay, aromatic carbons are attached with this alkene bond, and so we are affecting only with this alkene substituent. Okay, so this gets affected, this bond gets reduced with the deuterated compound. Thank you. If you have any doubts, you can ask me in the comment box.